Assalamu alaikum. Welcome to the presentation of our project CNN-based segmentation and classification of skin cancellation. In this project, we devised a transfer learning approach for dermoscopy lesion segmentation and classification. Skin cancer is a common form of cancer where skin cells grow abnormally. Skin cancer may develop in many regions of the body. It can form in the outermost part of the epidermis or squamous cells, inner part basal cells, or melanocytes. Based on where it is formed, it can be categorized in three types: basal cell carcinoma, squamous cell carcinoma, and melanoma. Pigmented skin lesions can be of various types. Most common types are melanocytic lesions, keratinocytic lesions, vascular lesions, and reactive pigmentation. Dermatologists employ conventional rule-based technique for skin cancer diagnosis, but this process is difficult, time-consuming, and erroneous. So, automated CAD system-based deep learning methods are getting popular.
The aim of our project is to segment skin cancer lesions from publicly available datasets, classify those images in combination with the segmentation network, and illustrate the efficacy of both segmentation and classification. As far as the graphical abstract goes, we take the encoder and decoder for the segmentation network to predict the mask, combine them with the classification network to predict the classification of the cancer lesions, keep the entire network learnable by classification, and optimize each stage thereby. For the segmentation network, we take inspiration from the EEE426 architecture but change the encoder backbone with efficient NetB4 network. To illustrate, the encoder architecture is formed by the double convolution from the first image to get X1, and the X2 to X6 are found from the efficient NetB4 architecture. As the decoder block is a repetitive block, it is shown here recursively, as dk and xk-1 come from the decoder block which is beforehand, and it outputs a dk-1. The final dk-1 is convoluted with a 1x1 kernel and a sigmoid to obtain the final mask. Towards the classification side, we take the external features coming from the encoder/decoder and pass them through an FCM block, the sizes of which are shown here. The FCM block, or the feature coalescing module, is illustrated here with a parameter of f. The final outputs of the FCM32 alpha block is passed through the 3D LR, which is the 3D layer residuals, as shown here. Finally, the residual R6 and the feature map Z5 are global average pool to get the dense layers, followed by some additional dense layers, which are concatenated and dense fully connected to get the final output lambda, which is our classification feature extraction output, parameterized by YJs and a filter multiplier alpha. Now, to integrate the classification feature extractor of the CFE to the segmentation network. First, we take the encoder features X1 to X6, pass it through a CFE with alpha equals to 16, as well as the main image, to get lambda E, 192 size vector. Then we pass the decoder feature maps D1 to D5, as well as X6 to the CFE with alpha 8 multiplier, as well as the image, to get the lambda D 96 vector. Then we concatenate those vectors and predict the output, which is the classification type of the cancer lesion. The entire network throughout this process is kept trainable.
For most of the experimental part of this project, the HAM10000 dataset known as the MNIST for skin cancer has been used for training and testing models. For our experiments, the dataset was given a train, validation, and test split of 80-10-10. Despite being imbalanced in nature, the 7 classes have an equal distribution over the 3 subsets. Metrics used for evaluating our subtasks are shown here. In the segmentation task, dice score was considered to be the main evaluation metric, and in case of classification, accuracy and macro F1 scores were considered. After training and comparing with several baseline models used for medical image segmentation, We can see from the graph that UNet models with DenseNet 121 and EfficientNet B4 backbones have the best performance in all the criteria. A high percentage of images have a DIE score greater than 95% with accurate prediction masks. More than 21% data have very good predictions. Less than 5% data have average scores. And very few complex samples have huge variations from the ground truth. When compared, our classifier model transfer learned from the best segmentation model is shown to outperform all the baseline architectures. In the confusion matrix of our best classifier, the prediction counts on the validation and test sets show that the number of true positive predictions are high, with the exception of NV, BKL, and MEL classes. Since a significant percentage of melanocytic nevi develop to the malignant melanoma stage, they have very identical visual characteristics, causing classification errors.
Now I would like to talk about some segmentation models that we developed and tested. Apart from the UNet BV1, 2, 3, and 4 proposed segmentation models, we also tried 8 other variations, UNet Backbone 5 to Backbone 12. All the changes are in the encoder part of the network. For example, UNet Backbone 5 has an untruncated EfficientNet B2 network as its encoder. UNet Backbone 9 has an untruncated DenseNet 169 encoder network, and so on. If we look at the accuracy, DIE score, and intersection over union performance metrics of our scrapped segmentation models, we can immediately see that their performance was not too far behind our proposed models. Although UNet Backbone 4 has the highest accuracy and DIE score, while UNet Backbone 2 has the highest checkered index on the validation set, some of the other models made comparable results. If we look at the test set, we get similar observations. UNet Backbone 3 has the best accuracy and DIE score, but UNet Backbone 8 has close results. However, UNet Backbone 2 is the only model with checkered index over 90%. We also tested 7 classification models. Model 1 consisted of a simple vanilla CNN feature extraction model which acted upon the skip connections from the encoder. Model 2 used the proposed CFE model with alpha equals to 16 and UNet Backbone 3 encoder variant for classification with encoder weights frozen. Model 3 was the same as Model 2 except for the encoder weights were set to trainable. Model 5 and 6 used M blocks described later for feature extraction, with Model 6 extracting features from both the encoder and decoder. Finally, Model 7 uses the CFE extraction network with alpha equals to 16 on both the decoder and encoder. Here we can see the vanilla CNN feature extractor. Subsequently, the layers are concatenated and then convolved and pooled, and the result is concatenated with the next layer. This ends into a feed-forward classification neural network to give the final output. Here we can see the previously mentioned M blocks, which also extracts features by concatenating successive layers and eventually forms a tree-like structure that terminates into a feed-forward classification neural network. Looking at the performance of the classification models in the validation set, we can see that Model 4 had the highest accuracy, while Model 7 had the highest F1 score. Once again, on the test set, Model 4 has the best accuracy, but this time Model 6 has the highest F1 score. However, the performances of all the models are quite consistent and stay within ±5%, except for Model 1.
We have also tested our method on a different modality of CT scan. Here, we are showing some visual results on the MUSMED COVID consolidation lung dataset. Our proposed method achieves a mean DICE score of 0.5714. The highest score on the validation set was 0.875 and the lowest was 0.005. Although we did not have CT scan data in our mind when we designed our algorithm, it achieves quite a good score in this domain, but it could not beat the state of the art compared to the existing works. For cost analysis, we demonstrate how much it would cost to collect the raw data and train the joint architecture. If we use a high-end imaging device like a DSLR camera and train it on an RTX 3060 Ti GPU, it would cost us about 2,12,000 taka. But if we go for a cost-effective solution to collect the data in consumer mobile device and train it on a free Google Colab, it would cost us about 10,000 taka. We also have some future plans for our project. We would like to further inspect the architecture and internal features of our model to see if we can make it more interpretable. We would also like to test the efficacies of our custom model on other biomedical tasks outside classification and segmentation. We are also looking forward to any additional task that is necessary to convert our work in an well-polished journal format. So thank you for attending our presentation, and we are happy to take any questions.